In today's deep learning video, we are going to be taking a look at how you can build your very own linear regression model within PyTorch. And this would be something I'd recommend as like your very first PyTorch model. I'm going to go line by line explaining everything that I do along the way. So that way you aren't confused, because I know when I first started studying PyTorch, I was confused and didn't understand everything that was going on. And this is going to be one video of many in a new PyTorch series that I'm going to be developing here on the channel. With that out of the way, I do recommend that you know a little bit about Python classes. I did just recently upload a video, so feel free to check that out if you're not too familiar with that. And with that, you should be ready to go. Let's start coding. All right, so I have a brand new Google Colab notebook. First thing we're going to do is we're going to import a few different libraries. So try to explain them as we bring them in. So import torch. Essentially, when we're using PyTorch, we're going to always have to import in torch. But then what we're going to do is import in torch.nn as nn. And you're going to see a little bit later, we're going to be building out a class. Essentially, we inherit for something that's going to be called nn.Module. So that's why we need this one. So next, we're going to import in torch.optim. And then we're going to call this as optim. And this is going to be our optimizer. We're going to be using something called SGD in this video. And maybe I'll make some other videos in the future based off of different optimizers, as well as what's essentially an nn.Module. But that's outside the scope of this first one where we're going over the linear regression. Next, we're going to import in NumPy. So import NumPy as NP. Should be familiar with that. And then we're going to just do some charting. So we're going to use matplotlib. So import in matplotlib.pyplot as pltin. I'd hope you have some familiarity with NumPy and matplotlib. Like, you don't need to be a NumPy expert. And also you just know the basics of plotting for this video, because PyTorch is quite advanced in comparison to these two libraries. All right, so I'm just going to run the cell over here. It'll take a second to connect, and then we will be good to go. And all these libraries should already be built in specifically into your Google Colab notebook, so you don't need to pip install them. All right, so now we're going to generate some data. So the first thing we're going to set up is going to be our X. So what I'm going to do for X is we're going to create an np.array. So we're going to create our array. And don't worry, we're going to change this into tensors in a little bit. So have your np array over here. And then inside over here, we're going to say X for X in range. So essentially, I'm going to be building out an array that's going to be 0 through 99. So put 100 over here, because in Python, we start at 0. And then, well, essentially, we'll have all these X's. Now, the next thing that we're going to do, and I'm going to make another brand new line, is we're going to reshape this. So I'm going to say X equals X.reshape. And we're going to reshape this from -1 to 1. Now, this is going to be a column vector and also a 2D. Now, this is going to be a column vector and also eventually a 2D tensor. And this is the format that we're going to specifically need for a linear regression. So even though that we have one specific data point, we're going to be turning this into 2D. It sounds confusing, I know. I'll show you the visuals in a second once we also build out our Y. So our Y over here, we're going to do a linear regression, right? So I'm going to say Y equals, I'm going to put over here 46 plus 2 times, and then we're going to have our X value, which I should make this a capital X, right? And I'm also going to put dot flatten. And this might be confusing, but we're going to turn our Y into a one-dimensional. So our X on here is going to be two-dimensional, right? And that's why we have original or NP array over here. And we reshape this one, so it's going to be a vertical on this side of things. And then our Y, right? First, we're going to do is flatten our X, so it's one-dimensional. And then we're going to multiply it by 2 and add in 46. So, sounds confusing. Let me show you a little bit more of a representation. So, I'm just going to put X here, and that way we can visualize this data. So, okay, we have our array over here, and you can notice that we have 2 brackets over here. This means that we're going to be working in a two-dimensional array. And you can see that it's a vertical array, right? We start from 0, we go 1, 2, 3, 4. That's because of this over here, x for x in range. So if you're not too familiar with this code, right, we're starting at 0, we're going all the way to 100. So we're going to print all the way to 99, right? We don't print out 100 because we stop at 100. So that's why we have this. And again, it closes over here 2 dimensions, right? So then if we build out a brand new line, let's put in our y specifically, you'll see that this array looks like this. And we only have one bracket because we are doing a one-dimensional array. And if you take a look at these numbers, so we start with 0, right? Let's go over here. 0 times 2 is 0. So add 46 to it, right? And we go back over here, we have 46. Then we go to 1. 1 times 2 is 2, plus 46, 48. So this works out all the way over here. We're going from 46 to 244. So what we're going to be trying to do is to build out a PyTorch model that takes a look at our values over here, right? 0 through 99. Looks at our values over here for y, 46 to 244, and essentially builds out a linear regression to predict results. And it's going to take a lot of code, and that is essentially what we'll be working towards. So let's get started with that. All right, and one last thing before we do end up building out this model, let's just represent this data through matplotlib. Now, what I'm going to do is we're going to build out our first chart here, and we're going to build out a chart at the very end with our predicted values. So that way we can see how close we are on that side of things. So we're just going to go over here, plt.scatter. Then we're going to say x, y. Then you can create a label as well. I'm just going to say our label on this one is going to be initial data, something like that. Okay, and I should be good there. You can do plt.title, and then we'll say like pre-PyTorch. Then we set our x and y labels. So plt.x label, throw in an x over here, plt.y label, set in our y on this side of things, set our legend so we can show this. It doesn't really matter too much. And then plt.show. And should take a second. And here we go, right? Just very basic linear regression. X goes from 0 to 99. And then this is essentially the correct answer on this side of things. So, all right, let's start working on this. So we have our data that we generated above, and we can get going. Now, the first thing we're going to have to do is turn this into tensors. And it's actually quite forward to do that, pretty easy. But I would recommend doing one thing. So when you're in deep learning, one of the most common practices out there is to normalize your data. Now, this data isn't normalized, so let's go through the process of specifically normalizing that. Now, you're going to need a few different things. First thing that we're going to need is to have our mean, and then also a standard deviation. So I just labeled these as x underscore mean and x std, and that's going to be equal to x.mean, and then also we're going to say x.std. Okay, and also just to show you, like essentially this is equivalent to if I went over here and saying x.mean is equal to this, right? Just a shortcut if you don't have the best programming skills. And I learn stuff all the time too. So that's essentially what this means. All right. Not to get off topic, but we're going to say x.normalized. That's going to be equal to, and then inside over here, we're going to say our big X minus our x.mean. So we're going to have this x minus x.mean, and then we're going to divide by x std, just like this. So what we're going to be taking a look at is we're going to take our value for x, we're going to minus the mean, which is the mean value for all these x's, and then we're going to divide it by the standard deviation. Okay. Then what we're going to do is we're going to create our tensor. So let's go over here. We're going to say x.tensor like this, and we're going to say that's equal to torch.tensor. And then inside over here, we're going to throw our normalized value. So we have x.normalized, right? Or x underscore normalized. And then we have to define our specific d type. So D type on this one is going to be equal to torch.float 32. All right, so we should be good here. I know we're having an error on this side of things, and that should go away. And great, we have that. Now, just to see what our tensor would look like, I'm just going to go over here, print, and there's a few different ways that we could do this. I'm just going to use like this, tensor.shape, and boom, right? Our size over here at 100 and also 1. All right, so now that we have our X working, we're going to do the same exact thing for Y. So literally just copy your code over here, because I hate repeating it and typing it all out, and just change it all to Y. So let's go across the board and do that. If you want to retype it out, if it's faster for you, go ahead. I'm not the fastest programmer by any means like that, and I'm also recording, so I don't want to make a mistake, which is very common. And we should be good on here. All right, and let's print out our Y tensor shape. So I'm just going to say Y underscore tensor.shape. And you'll notice our tensor size over here is just 100. Again, we're looking at a 2D tensor for our X, and we're going to have 1D for our Y. All right, so now's the fun part. We're going to be creating a class, and we're going to inherit essentially from something called nn.Module, and that's why we have this torch.nn up over here. So kind of connecting the dots on that side of things. Now, before we do that, I just want to say I have a 2-hour video on classes. If any of this is confusing, pause the video and watch the classes, because I think you should have that background before you move into PyTorch. So please watch that video if you don't understand how classes work, and then move on to this PyTorch series, because I think it's critical. So we're going to go over here. We're going to do class. We're going to do Linear Regression Model. And I'm not the best with classes. I'm still trying to improve my skills, so I'm just telling you as well on that side of things. So, all right. So we're inheriting from nn.Module, and we're creating a brand new class called Linear Regression Model. Now, the first thing that we're going to do is use something called a magic or also a dunder method, and it's going to be called init. And you're going to always see this across the board when you're going to be working with classes. And also something you always see is we throw in self over here. So we're going to do two things. We're going to have our in features and out features. So in features, and then also our out features like this. Okay. And now we're going to go into super, which also deals with inheritance. And then we're going to do dot. We're going to do init again. Score like that. And again, it's like a method. So we have to have that over here. And one last thing, we're going to do self.linear over here. It's going to be equal to nn.linear. So linear is part of this nn.Module. And what we're going to do is we're going to throw in here both in features and out features. All right, so we need to have one more method over here. We're going to define it as forward. And this is what you're going to be sometimes heard as like a forward pass. And we're going to throw in here self and also X. All right, and forward pass, you're going to need a forward in pretty much all your PyTorch models that you create. So we're going to do a return over here, and we're going to return self.linear, which is this over here, right? We talked about this. Then what we're going to do is we're going to call an X, and we're going to do something else. We're going to squeeze. And the reason why we're going to squeeze is we want to have a one-dimensional output. Now, if you remember from earlier, our X was two-dimensional and our Y was going to be one-dimensional. So we want to have that 1D final result on this side of things. So that's why we're doing this squeeze of 1. I know it's confusing and it seems tedious to have X over here, two-dimensional, and we squeeze at the very end. But yeah, I didn't make the rules. So we're just going to run this over here, and great. So a few other things that we're going to need for this model. So what we're going to do is we have to define our in and out features. I just prefer to have these over here as variables on the outside. So we can say in features equals 1, out features equals 1, because we're only going to bring in an X, right? And we want a Y as an output essentially. And then we're going to create our model. So we're going to say the model equals linear regression model. And then as we showed, right, we need to have our in features and our out features, which both these are right over here, right? So we have in features and also our out features of 1 each. Okay, so now let's run this. Great, now we're gonna move on to the next step. So we need to have 2 more things. So we're gonna define a criterion and then also an optimizer. So criterion over here equals, and then we're gonna go back to NN, which we imported, right? And we're gonna use something called the MSE loss, like this. Now, this is mean squared error. And essentially what this takes a look at is the average squared difference between predicted and also our actual values. And I'm pretty sure I've covered this a few different times in the channel and some of my other machine learning videos. Maybe I'll make just a video on different things like MSE in the future. Now, the next thing that we're going to do is an optimizer. And that's back over here where we use torch.optim as optim. Okay, so let's go through here and we're going to say our optimizer equals optim.sgd, and this is all capital on over here. Now, a few things that you're gonna have to put in here. So first thing we're gonna do is we're gonna put in our model parameters. So you just do model.parameters like this, and then you have something called a learning rate, and that's gonna be LR, and we'll put equals 0.1. And learning rate does have a big impact on your model, so feel free to tweak this specific number. Now, SGD is going to be one of your most common optimizers that are out there. And essentially it works like this. You're going to have your parameter equal to your parameter minus learning rate times your gradient. And maybe this is a little bit too much detail, but I just wanted to show you essentially how this SGD specifically worked. And this might be a little bit too much detail, but it's going to be essentially optimizing your model's parameters based off of this learning rate that we defined and also the different gradients of the loss function. All right, I'm going to just remove this code over, or remove this comment over here, run the cell, and we're going to be on to the next line. All right, so now what we're going to have to do is we're going to have our epochs, and this is how many times we're going to run through our model. So you can say num epochs, and we're going to say that's going to be equal to 10. All right, and this means I'm going to run our model 10 times. You can do 100, you can do 1,000, 10,000, but for this video, I will be doing 10. And here's why, because we're going to be creating a for loop to specifically run through this model. So what's pretty common is for epoch in range, and then your range is going to be this number of epochs that we defined above. So feel free to change this if you want, but this is kind of just standard within PyTorch. And the first thing we're going to do is our forward pass. So we're going to say our outputs equal, and then we're going to say model, and we're going to put in here our X tensor. And that X tensor is that 2D that we defined above, right over here. Not there, but our first part is our array over here, and then right over here, right? This X tensor, which essentially, like, we called this over here, but we transformed this to a tensor here. We're going to be using that as our input into our model, okay? Next thing that we're going to do is we're going to calculate our loss. So our loss is equal to our criterion. And what we're going to be taking a look at is our outputs and also our Y tensor. Our Y tensor has the final answer, right? If we go back above again, and I know this technically isn't a tensor right now, where this is at, right? This is our exact results that we expect to have, right? 46 through 244, and that's based off of the linear regression that I created above over here, right? Y equals 46 times 2, or 46 plus 2 times X. And then we flatten it, which also, I didn't even bring that up over here. I forgot when I was coding this video. If you know this reference, 46 and 2, let me know. All right, so Hopefully this is making sense. I know it's pretty complicated. But essentially we're taking a look at the outputs, right? Which is our predictions and also this Y tensor. Now, these next 3 lines of code, it essentially resets what we do. And that way we can have a more accurate model for each time we go up in our range or each time we go through these epochs, right? So the first thing we're going to do is clear the gradients. And that's over here. We're going to do optimizer dot 0 underscore grad. Okay. The next line is going to compute gradients. We're going to say loss dot backward. And lastly, we're going to update our specific weights in the different parameters. And that's going to be optimizer dot step. And you're going to see this all the time in PyTorch. So just remember the first thing we have over here, which I'll tab this out, with our forward pass. Then we calculate our loss. And then this over here is called your backward pass and optimization. Now, I just want to print out our optimization just to show you how this works over. So we're going to say for here, we're going to say epoch. Okay. And then inside over here, we're going to put our little brackets. Let's space this out a little bit. And we'll say epoch here plus 1. And don't worry what I'm coding over here. This is just to show you the visually what's going on. Number of epochs, which thank you for putting that over here. All right. And then we're going to have our loss and loss the item. And while I code this out, if you guys have not subscribed to the channel, I would appreciate it because these videos do take quite a while to make. And I'm only going to round this to 2. I think we should be good and make a lot of high quality videos, or at least I think I do. I'm just trying to document my journey going from as a data analyst to a data scientist, and there's so much to learn, but boom, there we go. All right. So this is great, right? It shows you every time what our loss function, and our loss function decreases, right? We start at 1.22, 0.78, 0.5, 3.22, 0.13, 0.8, 0.5, 0.3, and 0.02. And right, run 1, run 2, run 3. So we can see that our model is getting better every time we run. So like, if I really wanted to go over here and change this, let's say I made this 20, we're going to get even closer to 0. So let me just run that over here. And let's see what happens if we go to 20. So this time, right, we go to 0 on this side of things. I'm just going to put it back to 10. Doesn't really matter too much to me. And, right, we have our loss being 0. Great. Okay. So I want to show you that this worked. And also, I think it's good just from like a practical standpoint to see specifically like how you would test your model. So what we're going to do is we're going to say new underscore x equals to, and put whatever number you want, right? I'm going to put over here the number 121. Now, what we're going to have to do is normalize our x. So we can say new x normalized equals, and we're going to go through the same process, right? So first normalize your value. And I guess you could technically make this into a function and make everything super easy, but you know what? We're just going to walk through this. All right. So again, go over here. We're going to take our new x minus the mean, divide by the standard deviation, blah, 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 basic stuff. All right. Now we're going to create a tensor. So new x tensor equals torch dot tensor. Throw in here this new normalized value. Okay. Put that in here. Awesome. Put our D type. So D type. This equals torch dot float 32. I believe we put a little bit above. And then I'm going to transform this. So we're going to just do a dot view 1 and -1. Okay. Up next, what we're going to do is make our prediction. You can put your model in something called eval like this. So it's evaluation mode. It's a little bit different than when we're training. And then we're going to have another line over here with torch.noGrad because we don't need to perform the gradients anymore. So, and it's better for your memory as well. Make sure it runs faster. And what we're going to do is prediction normalized equals model. And we're going to throw in over here this new X tensor. So our prediction is going to run in here the model, and we're going to have this new X tensor that we created, right? Again, we just called X essentially 121. We normalized it like we did above, and we created a tensor. Nothing too crazy, right? 3 lines of code. Then we put our model into evaluation mode. We didn't want to have these specific gradients, which the more I code, the more I think I need to have just a basic PyTorch video explaining like different terms and stuff like that. Maybe a little bit of math too. So our prediction right now would be normalized. So we need to get our actual value now. So I'll show you how we can go backwards. Not backwards in the PyTorch sense, but backwards of going from normalization to non-normalization or denormalized value. So what we can do is prediction denormalized equals, and we have our prediction normalized. And how you do this is you grab your item. So dot item like this, okay? We're gonna times this by our Y standard deviation. Remember, now this is our Y value that we're predicting. We're no longer on the X, right? We're on Y. So we're gonna use our Y standard deviation. So we're gonna multiply it by Y standard deviation, and we're gonna do plus Y mean. And I promise this maths out. I don't even know if it's a proper sentence or not, but I promise that this math works on this side of things, and you can do algebra to check it, but I'll save you some time. So now let's print this out. So we're going to say print over here, and we're going to say predicted, I'm horrible spelling, but predicted value for X equals, and then over here, what we can do is say our new X, which we have over here. Okay. And then what we're going to do, throw in here our prediction like this. Now our value should be, let's do some math, right? 121 times it by 2. So we're at 242. And then we are adding in, what was it again? It was 46. So we're at what? 242 plus 46, 242, 82. We should be at 288. So let's see how close we are. 287.977. That's a pretty close value, but that is not exactly 288. So I bet you if we increased our epochs over here and let this train even longer, would have a more accurate result. But with the value of 287.97, I think that's pretty valuable. We'll do a recap here at the end. But I also just want to show you, we can have our original data, and then we can take a look specifically like what we did with PyTorch and build out another plot. So let's do that. So we can first do our scatter plot, which honestly, I probably could just be lazy and copy some of this. So we don't need anything different on here. We can say like our initial data. Then we can build a line. So we'll say like fit line equals model. Throw in our X tensor and detach NumPy. Okay, we're going to do times Y std plus Y. I actually just put this in the chat GPT to essentially build this out because I was kind of lazy on the coding side of things. But this again kind of denormalizes those predictions. We're going to do plt.plot X, throw over here this fit line. If I can actually copy it correctly. We're going to say over here, this is going to be in red, which is our label equals PyTorch line like this. Grab this legend. Oops. Should be good there. Still need our X and Y. That. And we'll change our title on this one. PyTorch with predictions. I'm just going to fix that over there and we should be good. And did not work. Tensor has no attribute detach. And that's because I misspelled it. So it's DETACH like that. This should work now. And check that out. So fairly accurate. Not exact, but I think we did a fairly good job. So to kind of explain what we did in this video, and I know it's probably getting a little bit longer. First, we brought in a few different libraries. So try to be familiar with these three. After this video, like takeaway, like you're going to be using these a lot. Then we generated our values. So generated X and also Y with this 46 and 2 reference over here for our linear regression. Our X in a linear regression needs to be 2-dimensional. Our Y has to be 1-dimensional. You can see that this is 2-dimensional with these 2 brackets. And also we have our vertical on the side of things. Now, also, I should bring this up. There's a lot of things to learn about PyTorch, but you need to make sure also that you can do matrix multiplication because that's essentially what we're doing here with some of the math in the back end side of things, which could be another video. But if these aren't compatible, you're going to have errors. So maybe I'll talk about this in another video, like the linear algebra behind this, but make sure that it's compatible. And by making our X vertical like this, makes it compatible. All right. Just plotting doesn't really matter. Then what we're doing is normalizing values, something that's very, very common and frequent within PyTorch and deep learning in general. So we did that over here for X and also Y. You can see the tensors now because we had NumPy arrays, but you can use NumPy arrays within PyTorch. Super, super easy. So like I recommend just building your NumPy arrays and then transforming them into tensors like this. 2 seconds, right? Like 1 line of code. And then we built out our linear regression model class. We inherit from our nn.Module. We create our init dunder method over here, right? Self, we have our in features and then also our out features. You use your super. So that way we inherit from nn.Module, which actually, if you want to see the documentation too, which I would recommend, check this out. You can see why, right? So torch.nn and linear, you need to have your in features and your out features, right? So that's why we have in features and out features. You go here, self.linear, right? Equals nn linear in features, out features. Okay, hopefully this makes sense. We have our forward pass over here. So to find our forward pass, we also have our self and also our X, and we return our linear X over here. In features and out features, we define these on the outside, right? We call in our model, our linear regression model takes a look at our in features and out features. Then we have our criterion and then our optimizer, okay? So criterion takes a look at this loss. Our optimizer optimizes our model's parameters. This tells you how many times we want to run through our model. I just put down 10, so it runs pretty fast for epoch and range. So this runs all the way through this, right? 10 times. That's how this range specifically works, 0 through 9. Not that matters, but we have our forward pass. So our outputs equals the model. We throw in our X tensor over here, and then we calculate the loss associated with it. So we take a look at these outputs in comparison to our Y tensor. Y tensor has the exact values. Our outputs does not, right? But it learns over time. The more and more that we run the model, the more accurate it's going to be. So that's why we have that there. And then you need the backward pass and optimization. And that's why we have optimizer.0grad, loss backwards, optimizer.step. And then you don't need this code. I just put it over here on that side of things. Now, what we're going to do on this side of things is see how accurate our prediction is. So I threw in a value here to predict. Again, you can essentially make a function if you really wanted to, and just call in specific numbers into this function, but like whatever, like I'll just show you how to do it. Then we have to normalize our x value. We have our changing of it. We're going to go 1, -1, right? Then we over here, we put our model into evaluation mode, no grad, so that way you can run a little bit faster, better on memory. Normalized prediction, right? Model, we throw in our new tensor, which we created over here, right? Denormalize our value. We're using y this time because put in x, we expect y out. We predict our value, we print it out. And then just this code over here, right? Scatter, we already had this earlier. We did a fit of our line, which like I said, I literally just generated that over here. But I mean, it's not too bad on this side of things, right? Plotted that in red. Just did some basic matplotlib, and here we go. Hey, I hope you guys enjoyed this video. It took quite a while to research and then also code this up. So if you did learn something new, make sure to subscribe to the channel and feel free to share it with a friend because that allows YouTube to help promote this channel. Now, if you're a PyTorch expert or deep learning expert and I made any mistakes, please let me know. I'm by no means an expert, but I'm trying to improve my skills every single week. And that's why I'm going to continue to upload videos towards the end of this year and also a lot next year with fundamentals of PyTorch and also more models. So be on the lookout for that, as well as more LLM videos in 2024. I'm super excited to improve my skill set and hope you guys do as well.